you might see these two names together and think, oh God, Charlie's going to talk about the initial mass function again. Turned out that Peter and I were also a little bit tired of thinking about the initial mass function, so we wanted to think about something else, and we started thinking about how, how to keep these dead galaxies dead. And I think one of the more striking things that we've seen from the observations that I'll explain more later is that these galaxies emerge at remarkably early times and somehow maintain being dead for very long times. I wrote the title of the talk was written fairly carefully, in particular the word maintaining rather than quenching, and stellar heating rather than stellar feedback, and I'll explain later why I chose those particular terms. So just for orientation purposes, the main question here is why do these types of galaxies exist, right? Especially these massive, quiescent, early type galaxies. There's two issues associated with this that perhaps are unrelated, and there's been, I think, relatively little discussion of these two issues, especially compared to years past, I think, at this workshop. In particular, how to turn these galaxies off. So that's like the first step. And then how to keep them turned off is the second really important step. In particular, the second step, I think, hasn't been discussed very much so far this week. Now, I'll just give the sort of standard lore. And we can discuss whether this should be standard lore or what have you. But the basic idea, or one at least straw person idea, is that there's this quasar mode feedback, this basically thermal bomb that goes off in the middle of the galaxy, rips apart the cold ISM, and turns the galaxy off. Right? It gets rid of all the cold gas. We've heard other ideas that maybe the gas is just exhausted. It's just consumed. There's no more cold gas left. Or maybe there's something like morphological quenching, where the gas isn't able to go unstable and form stars anymore. Somehow you need to turn the gas off. But then the second sort of long-term issue is maintaining that quiescent galaxy. And this is sometimes referred to, at least in the context of AGN feedback, as radio mode feedback. Like radio bubbles being ejected by AGN, heating the diffused hot atmosphere. So the basic issue is that even if you quench this galaxy, especially big galaxies which reside in large dark matter halos, those dark matter halos are filled with hot diffused plasma, and that plasma should cool on cosmologically interesting times. In the cluster community, this is known as the cooling flow problem. And this literature goes back decades. Just as an example of how this works, this is a semi-analytic model from Rachel Somerville. This is the stellar mass function. This is observed down here. If you just converted all of the baryons into stars, you'd have this mass function here. If you have some model with no feedback, you get this dotted line here. Supernova feedback helps the low mass end, but that gives you this dashed line. And AGN feedback is really what helps turn these big giant galaxies up here to be a little bit less massive. One more quick slide on this radio mode feedback. This was really popularized by the semi-analytic model from Darren Croton and company. This is the mass cooling rate at 4 different redshifts, both with and without this radio mode heating. So you can see it's at the highest halo masses where this heating mode is supposed to be most effective, and it's supposed to be more effective at lower redshift. And this is sort of by construction in the model. There's been some interesting recent developments on the observational side that maybe helps to motivate what I'm going to mention in a few minutes. And that is that it turns out that whether or not a galaxy is quenched, whether or not it's not forming stars, seems to be more strongly correlated with the galaxy's structure than with its overall mass. And this has been known for a while, going back to early Sloan work from Guinevere Kaufman. This is basically quenched probability, the function of central concentration of stars in these two metrics here. This was looked at it again in the Candle survey and in Sloan. The basic point is that if you rank objects by mass, there's very little correlation between that rank and quiescent fraction. But if you rank by velocity dispersion, surface density, or a Sirsic profile, some kind of shape parameter, you have a much stronger correlation with quenching. So it's really the distribution of the stars rather than their total number that seems to be a really strong proxy for whether a galaxy is turned off. The second interesting development is that we find these quiescent galaxies all over the place, even Redshift 2 and beyond. And that's also pretty interesting and relatively recent development. OK, so I'm not going to mention the IMF, but I'm going to mention stars, and not the big, massive stars that Phil and Mark were talking about. These are more piddly stars, your average run-of-the-mill fellas. Stars less than 8 solar masses. They don't go supernova when they die. They die quietly. They eject their outer envelopes in a superwind phase after the asymptotic giant branch, and they evolve to high temperatures in the Hertzsprung-Russell diagram, and eventually cool and become white dwarfs. These are known as post-asymptotic giant branch stars. This is a beautiful image in the ultraviolet of the Mira asymptotic giant branch star. It's moving this way. You can see it's shedding tons of material. It's just really nice evidence that stars lose lots of mass. And here's a rogues gallery of beautiful planetary nebula. Just for those of you who haven't thought about this stellar evolutionary phase ever, or since your stellar evolution class, one slide overview. So this is a Hertzsprung-Russell diagram, luminosity, temperature. The 3 lines are 3 different isochrones for different ages. So it's a range of stars, all at a given age. The blue line are stars at 10 to the 8 year. The red is 10 to the 10. You have your main sequence, the giant branch. These are these thermally pulsating AGB stars you've probably heard too much about. And this is the post-AGB phase over here. So these are stars that they evolve at approximately constant luminosity, reaching temperatures of order 100,000 Kelvin. And then they come down here to the white dwarf cooling sequence. They can become planetary nebulae when they reach temperatures in excess of about 30,000 Kelvin. You expect about 1 of these stars for every 10 to the 7-ish stars formed. So if you have a galaxy with 10 to the 11 stars, at any time we'll have 10,000 post-AGB stars. This just as an advertisement, these are new isochrones that we're creating here at Santa Cruz. This is being led by a grad student, Jian Choi, who's in the audience. We're calling these the MIST isochrones, stand for Mesa isochrones on stellar tracks. These are going to be really the most complete isochrones that have ever been created, from the hydrogen burning limit all the way to the maximum stellar mass. So they're really great for a lot of applications, including this one here. These stars, the purposes of this talk, are interesting for 2 reasons. They provide 2 different kinds of energy. First, in these mass-losing winds that they produce as they die, the winds come off at a velocity of about 20 to 30 kilometers per second. And their mass loss rates at the very end here reach 10 to the minus 4 solar masses per year. So in 10,000 years, they'll eject the whole solar mass of material. It's pretty catastrophic. And on top of that, they produce copious amounts of ionizing radiation. So when they sit over here, they're shining at 100,000 Kelvin. So they're really quite bright objects. Now, as it just showed here, they traverse this phase extremely rapidly. Of order 100 years, they come across here, and then they go slower here. And they'll spend maybe 10 to the 4 years in this regime here. So it's a pretty fast evolutionary phase. There are major uncertainties with modeling this phase, mostly to do with mass loss rates. Let's take an example of how damaging or interesting these types of stars might be for a typical massive galaxy. So let's take a quiescent galaxy at Redshift 2. Stellar mass, we've estimated for these objects, are of order 10 to the 11 solar masses. They're quite compact, have half-light radii of order 1 to 2 kiloparsecs. They have fairly high velocity dispersions of order 300 kilometers per second. It's one-dimensional line of sight. And based on all this discussion about stellar mass, halo mass relations, we infer they have a halo mass of order 10 to the 13 solar masses. Okay? If we just take the number of stars here, we can get an estimate of the number of post-AGB stars there should be. If we do some ballpark sort of back-of-the-envelope calculations of so these stars having luminosity about 10 to the 4 solar luminosities and a temperature about 100,000 Kelvin, you expect an ionizing luminosity from all these stars of about 10 to the 41.7 ergs per second, and that's consistent with more detailed stellar population models. In addition, the energy input rate from the winds is significant, not because the velocity off the photosphere, off the star is large, but because the random motions are so large that when these winds collide with any diffuse gas, it's going to shock, and so it'll have a huge energy deposition rate just because of the sigma squared here. So this is the sigma of the galaxy, because the typical difference of the velocities of the stars. And that can be of order 10 to the 41.3-ish ergs per second. Okay? If you now compare this to the cooling luminosity, and this was all, I should have emphasized, this is all kind of simple back-of-the-envelope calculations just to demonstrate sort of the level of interest here. If you take a 10% gas fraction, assume all that gas is in hydrostatic equilibrium with an NFW halo, and all that gas is at the virial temperature of the halo, just to get a sort of estimate of the cooling luminosity. The cooling radius for such a halo is about 30 kiloparsecs. So interior to that, the cooling time of that gas is less than the Hubble time at Redshift 2. You get a rate of cooling rate of about 10 to the 41 ergs per second. So these numbers are all comparable, and that's interesting. All right, we were pretty excited by this. We were working on this workshop in Leiden. We got really excited. And as with any idea that you think is great, turns out it was done 40 years ago. In this case, interestingly, it was done by Bill Matthews and collaborators for many years. I think to some extent they were addressing different questions, and I think for some reasons that I haven't had a chance to talk to Bill about it yet, has fallen out of favor, at least. Well, anyways, I'm not sure about the details. But I think it was appropriate, sort of oddly fitting that this week we were kind of honoring Bill, and it was, anyways, this was serendipitous. Just to give you a little more detail about how this can affect galaxies throughout the stellar mass halo mass plane, what you're looking at here is the relation between stars and dark matter halos. Obviously, no galaxies can live up here. This is at Redshift 2. This is the rough stellar mass halo mass relation at Redshift 2 from Peter Baruzzi and company. And so you can now do the same exercise we did here at each point in this diagram, each stellar and halo mass combination. And you can compare the cooling luminosity within the cooling radius to the heating rate available from ionizing photons and from winds. And you get the following here. So the blue is where cooling wins, and the red is where heating wins. And the gray region is where you're in a plus or minus factor of 2, so it's kind of the transition region. And the interesting point is that in the regime where we see a lot of quenched galaxies, the sort of bookkeeping works out such that the energy available from these types of stars, in principle, can at least globally balance the cooling luminosity. So that's pretty interesting.
Try calculating the cooling rate.
So what we're doing is we're assuming that there's diffuse gas. It's these same assumptions. The diffuse gas, 10% gas fraction, it's at the virial temperature of the halo. And we compute the cooling luminosity interior to the cooling radius. So the stuff that can cool within a Hubble time at Redshift 2.
The baryons have an NFW density profile?
The dark matter has an NFW density profile. The baryons are in hydrostatic equilibrium. So they're more cored in the center. Yeah. So again, it's a toy model just to sort of illustrate the effect.
You allow the gas to sink in to one?
No. We just put it in hydrostatic equilibrium.
Okay.
Right.
And that will change. This simulation, by Daniel Wang and his student doing exactly, this distributed feedback in early type galaxies, and then the cooling will continue.
Yeah, no, I don't doubt that this is supposed to be just purely illustrative, right? at Redshift 0, we know that the temperature profiles don't change more than by, a modest amount from the virial temperature. So the temperature profile is not, assuming virial equilibrium of the temperature is not a terrible assumption, but indeed the density profiles will not be as simple as what we described here. The basic point is just that, at the knee in this stellar mass halo mass relation is right where you get to a transition between cooling winning and heating winning. What's also interesting is that in the cluster scale, you can't win with this also, which is also interesting because it's in clusters where we see the most dramatic evidence for sort of radio mode feedback and things of this nature.
In fact, for the group scale, if you had 50% gas fraction assumed, would it still go?
So 10% of the halo mass. So it can't be more than 17. So we're putting in a lot of baryons.
Oh, okay, good.
It's pretty baryon heavy. Yeah. So sorry. So I should have said 10% with respect to, yeah. Another way of looking at this is at a sort of somewhat more local requirement. So if you look at this, if you think about the density of stars versus the density of gas, the way this was estimated was, at what point in this plane do the Stromgren spheres at individual post-AGB stars overlap? So you need them to you need the ionizing photons to sort of, smoothly heat the whole region. And this is the region where post-AGB heating is effective. This is schematically where these compact Redshift 2 quiescent galaxies reside. We know their radii well, so we know this axis. We don't know this axis very well. This is where Redshift 0 to 2 star-forming galaxies reside based on inverting the Kennigan-Schmidt relation and observed size-mass relations and so on. I thought what was interesting is these objects down here. These are Redshift 0 galaxy groups from Ming Sun et al.'s catalog. And they're labeled according to whether or not they have extended H-alpha emission as based on Mike McDonald's wonderful H-alpha survey. So it's not surprising that obviously things with higher gas densities have higher H-alpha emission, but what's kind of interesting, at least anecdotally, is the line happens to correspond to this transition between the red here and the white here. So as an example, these are two objects from Mike's survey. This is imaging continuum, X-ray, and H-alpha. This is one of those galaxies that's in the cooling regime. You see this very extended filamentary H-alpha cooling. And up here you see no evidence for anything going on. So kind of anecdotal, but kind of interesting, I think. How much time do I have? So another question you might ask is, how does this heating rate compare to the 1A heating rate? At Redshift 2, just the sort of doing the typical supernova rates we think exist as a function of time, the heating rate's comparable. But what's interesting is that by Redshift 0, these post-AGB stars win by an order of magnitude, and that's just because the delay time distribution of the 1As goes down with time. So one of the nice features of these post-AGB stars is they're not very time dependent. They're just a heating source that just kind of happens at a constant rate at all times. The 1As go down by 1 over t, so it becomes harder to use these things to do much work at lower redshifts. For those of you who don't think about post-AGB stars very much, you might think, well, this is a lot of UV emission. Is it consistent with the data? It turns out it is. What you're looking at here is the stacked SED of quiescent galaxies at redshift 2. This is from Fumagalli et al. This is the points here. And the blue and the black lines are two different models for the post-AGB emission from these quiescent galaxies. And just the basic point is that the amount of flux we're saying is coming out of these galaxies is perfectly consistent with the observations in the ultraviolet. Now, one of the key aspects of this story is that the circumstellar shells around these post-AGB stars is being stripped, ram pressure stripped, as they move through the hot dilute gas. And it's these shells that in the Milky Way provide, make planetary nebula. So what you would predict is that as you go to these more massive systems, you don't see planetary nebula. The stars are still there, but they don't have shells that you're illuminating. And that's what you see actually in the data. This is the specific frequency of planetary nebula. It's a function of galaxy velocity dispersion. And you see that the relative numbers of planetary nebula goes down as you go to more massive systems. So maybe that's evidence that these circumstellar shells are being ram pressure stripped. I mean, there's other things going on here. It's not a smoking gun, but it's an interesting thing. This is a clear prediction of the model, that as you go sort of inward within galaxies, within massive galaxies, that you should see fewer and fewer planetary nebula. That observation hasn't been made yet because it's kind of hard to do. People haven't, I guess, cared to look for such things in the nuclei of ellipticals. We also see abundantly in nearby elliptical galaxies massive low column density H1 disks. And it's not entirely clear, A, where these things come from, and B, why they're not forming stars, why they stay at such low column densities. And one possible explanation is that the UV radiation from the old stars is providing some low-level heat to these disks, keeping them from cooling. In addition, it's been known for a while that you see spatially extended emission lines at low levels in a large number of early-type galaxies. And you see these emission lines at large radius. And the emission line ratios are indicative of non-H2-like emission line ratios. So this is the emission line ratio N2 to H alpha as a function of radius for two types of early-type galaxies. And these are kind of liner-like emission line ratios, but they're not in the nucleus. And so the canonical interpretation has been that these emission lines are powered by post-AGB stars. So we see direct evidence for some low-level effect of post-AGB stars in very nearby galaxies. So we know they're there and doing something. That's sort of good news. This model makes a number of fairly straightforward implications, which are easily testable and observable, which is why I like, sort of it is at least like a counterexample to other types of heating. One is that there should be a strong correlation between the probability of something being quenched and the stellar density and/or velocity dispersion, because those are the key variables in the problem, rather than, say, just total mass. There's little intrinsic redshift dependence, as I mentioned, but it does require a hot halo, of course. Any one of these maintenance mode type mechanisms, whether radio mode feedback or what have you, requires the existence of a hot, stable atmosphere. And as I alluded to in the very beginning, this is not feedback. This is just a heating source. So there's no feedback loop going on. It's just a flux of heat. So that's worth keeping in mind. And as I mentioned also, you expect fewer planetary nebula where this effect is where this is happening. So in the central regions of elliptical galaxies, for example. You should still see the naked UV sources. And with Hubble, you should be able to resolve them individually, actually. So you should be able to see these individual, quite luminous, UV bright sources. So observing this effect of stripping off the envelopes, leaving behind these naked UV stars, should be sort of really directly testable with Hubble, fairly straightforwardly. So that's a really sort of straightforward thing to test. I want to just, by way of conclusion, lest this sort of be misconstrued, I don't want to say that, well, we can just throw the AGN out the window. I mean, we're almost certainly doing something, right? And you can see clearly in Perseus, they're having some effect on the diffuse gas. You see in Fornax these giant radio bubbles. I mean, obviously, AGN do something. I'm not trying to say they don't. Although, just to sort of poke I guess, Phil's other eye out. The lobes are happening at these lobes are a very large radius, right? And it's not entirely obvious that the energy is actually being dumped in the central parts of the galaxy where you want the energy to be dumped. So anyways, this is just one of many issues with this radio mode AGN feedback. OK, so I wanted to just present a simple idea that, in fact, is a very old idea, but I think it's worth revisiting. I've talked to a few of you already about implementing this in simulations. I think it's straightforward, at least to sort of do it in a sort of approximate way. I think it'd be really interesting to see the effect that it has on the hot dilute gas in groups and clusters. So again, the stellar heating from these post-AGB stars offers a possible alternative to radio mode feedback, or at least it's going to help radio mode feedback or any other kind of sort of maintenance mode. These stars exist. We see them. So this heating term must exist in the real universe. The only question, of course, in detail is how much, and how some of these more detailed microscopic issues play out in galaxies. And one of the nice advantages is really a number of very clean observational predictions and implications. And there's a number of, I think, kind of exciting and fun numerical problems associated with this, like the detailed way in which the winds and the ionizing photons interact, and how they inject energy into the hot diffuse plasma. And the big uncertainty here that I also want to flag is the lifetimes of these post-AGB stars, which is not actually very well known. But again, it's something that you should be able to calibrate in the local universe by just going and counting UV bright stars. There hasn't been a very strong reason to do so, aside from those who just intrinsically love these stars. But I think this is another thing that we can actually solve in the nearby universe. So anyways, that's all I wanted to say.
Okay, so in fact, if let's say you look at these bright elliptical galaxies in, say, the central clusters, and in fact, you have probably more stars in the halo than what you see directly from the galaxy itself.
So you mean like intercluster light, for example?
Yeah. And that will also do this, right? Because this, that actually will make the things even more distributed, this energy source, and that may, just may help even more.
That's right. And in fact, I didn't dwell on this point, but in this diagram, sort of more local diagram, you've got the quiescent galaxies up here. What I'm plotting here and here are at two different physical scales. So up here, you're talking about like at 2 kiloparsecs, so really kind of in the middle of the galaxy. Here, this is measured down at 10, 20 kiloparsecs, so it's much larger. So indeed, I mean, at even larger radius, you do have these intercluster stars that will also be doing this as well. And it's a question of which one's going to balance at the end of the day.
So, Charlie, question. So, if you still expect to have dust inside the gas for this gas, do you expect the post-AGB stars to hit the dust enough to see further emission?
It's not clear if the dust will survive this process. And that's something else that Bill and Fabrizio have looked into, I think, a little bit. But when you look at, my understanding, when you look at planetary nebula, they're not particularly dusty, and that's probably because the dust is destroyed. So.
Two questions. One, this is a great maintenance mode for quiescence. Do you think this is actually causing quiescence?
No.
The second issue is how this is great to implement in simulations, because it doesn't mean you have to do all kinds of detailed modeling in the AGN, which is always problematic for lots of reasons, including how the energy gets transferred. Can you say in more detail how we should model it?
Well, in fact, there's going to be a talk on tomorrow, I think, by Raul. We were just talking. He's implementing the ionization part of this problem already. So, I mean, there's two ways to do it, I think. On the extragalactic scale, when you're doing multiple galaxies or cosmological, all you can ever do is the heating rate that goes to the stellar density. And there you can just do simple calculations. That's the kind I described. If you want to do it more locally and actually follow the interaction of the shell with the diffuse, then you've got to go talk to Mark and do a more local. I mean, that's a different. Depends on what you want to actually resolve versus just sort of put in by hand. But those are the two regimes. Like whether or not you want to resolve the wind interaction directly, or just say you've got some approximate for how much that wind's going to dump as a function of stellar density. But I don't think it's good. This is not going to quench galaxies, right? And that's kind of gives you a sense just from this diagram here. When you've got a cold disk, you're way over here. I mean, this is not going to stop a galaxy from forming stars. It's going to keep it from going back.
Once you have, as you said, you need the hot halo, and obviously have to not have a lot of cold gas in the disk, otherwise you keep
Right.
warming
I mean, the question that
that you're going to prevent the cooling of gas from the halo.
right. So I mean, the real question was, you see these quiescent galaxies at Redshift 2, fine. They died somehow, but they're sitting in the nodes of the cosmic web. They're going to be sitting in a hot halo for 10 billion years. Why the hell aren't they forming any stars? So that was kind of the motivation.
So it's probably a stupid question, but the AGB phase is not so well understood. But what's interesting, to me anyway, you showed the isotope for it. It moves across a very large part of the HR diagram. You said in 100 years.
Of order, 100 to 1,000.
Is it actually possible to watch resolved AGB stars move along that track?
Yes, it is. Look up Sakurais object. This is a star which has come down here and jumped back up. Because there are some stars that if they have a little bit of material left in their envelopes can reignite hydrogen. And so they'll do these loops around, and we've actually seen one in real time go from here back up here. So you can actually watch this in real time. It's very cool.
Phil? Yeah, so there was this series of papers by Giotti and Ostraker and Novak on modeling a bulge which had a mass loss rate, and they did account for the kinematic, the kinetic energy from the relative motion. They assumed essentially half m sigma squared, but they didn't include the ionization. And they actually argued that the mass loss from stars generated a cooling flow itself in the center of the bulge.
Yeah.
Which fuels the AGN. That's the key idea.
Right. So yeah. So I mean, this is kind of what I was alluding to when saying that you've got to. It's an unsolved. It's not clear what's going to happen to the material as it interacts with the diffused gas. I mean, it might just cool and then just contribute to a cooling flow and make the problem worse.
So the gas
Yeah.
loss rate can be calculated so that you can compare with the total amount of X-ray gas in halos. You can just maintain there or just pile up there, or in fact you have outflows.
So the amount of, if you just distribute baryons in the halo as we did simplistically here, then within 10 kiloparsecs, that hot gas is going to dominate over the mass returned from stars. So there should be a perturbation on top of that diffused gas.
Okay, I think it's time for coffee and some cookies. Let's thank Charlie again.